All right, folks. So last class we were talking about Postulate 3 and measurement. And what we saw is that we could define measurement in terms of any kind of general measurement operator. And then we looked at distinguishing quantum states, and we saw that you can't reliably distinguish non-orthogonal quantum states. So there's an interesting corollary to Postulate 3. We'll call it Postulate like 3 prime. And it's about projective measurements, which are specific type of measurement where you're dealing with an observable M that's a Hermitian operator, orthogonal. And the state of the system being observed is therefore a lot kind of more restricted. So the observable has spectral decomposition, as we talked about last class. So M equals the sum over little m, the measurement outcomes little m, times this value P of M, where P of M is something we call the projector, onto the eigenspace of M, and the eigenvalues are little m. So the possible outcomes of the measurement correspond to the eigenvalues, which are the little m's. And when we measure the state, the probability of getting the result is given by P of M. The probability is just equal to this inner product. Very simple. And given that that outcome occurred, the state of the quantum system immediately after measurement is just equal to the projector times the state divided by the square root of the probability. So this is, I mean, it looks a lot like what we did last class, but we kind of simplified things in numerous ways that allow us to write down some pretty nice properties of these projective measurements. So in particular, it's really easy to calculate average values for these projective measurements. So the average value of a measurement, I skipped a bunch of stuff. Let's just write it as E of M is equal to the sum over the little m's times M times the probability. So that basically, we can expand it out, gets you to this form. So the average value is equal to the inner product of the state with the measurement operator. The standard deviation of the measurement then can be written as I have it expressed here. So delta M squared is equal to M squared minus M squared. How do you say this? And this standard deviation is a measure of the typical spread of the observed values when you make the measurement of M. So if we perform a large number of experiments in which the state is prepared and the observable capital M is measured, then the standard deviation delta M of the observed values is determined by the formula, well, just the square root of this. So equals square root of M squared minus M squared. So this formulation of measurement and standard deviation is nice because it is kind of a really logical step to deriving the Heisenberg uncertainty principle yourself, which I think you'll get to do in your homework. So let's look at an example, just for completeness sake. So if we look at a measurement on a single qubit, let's think about measurement of the observable Z. So what are the eigenvalues of Z? 1 and -1. And what are the eigenvectors for those eigenvalues? We have 0 and 1. So if we are gonna make a measurement of Z on the state, let's pick one, psi equals 0 plus 1 divided by the square root of 2. It's one of our favorite single qubit states. So this is going to give the result plus 1 with a probability of a half. And it's going to give, so this is just equal to psi 0, 0, psi. And we'll get the result minus 1 with a probability of a half as well. So that's why we like projective measurements. They're very simple. Let's talk about phase for a minute. So physicists like to use the word phase in lots of different ways. And in this class, there's kind of two contexts in which we will talk about phase. The first is kind of written at the top. If we consider the state e to the I theta times psi, we say that this is equal to the state psi up to, so they're equivalent up to something we call the global phase. And it's interesting to note that the statistics of measurement predict that these two states are the same. So if we suppose that we have some measurement operator, m sub little m, associated to some quantum measurement, then the probabilities for getting our outcomes are going to be psi, the inner product of psi with m dagger m in one case, and it'll be psi e to the I theta, e to the minus I theta m dagger m e to the I theta psi in the other case. And these two things are equivalent. So from an observational point of view, these two states are identical. This makes sense because observable quantities are just the probabilities. And if we think about complex numbers and their amplitudes, a complex number z, that probability amplitude is just z squared, which is just equal to r e to the I theta squared, which is r e to the I theta times the conjugate minus I theta, which is just equal to r squared. So it doesn't care about the phase theta. Okay, so for this reason, when we have these global phases e to the I theta in front of our quantum states, we can ignore them. They don't change anything about the physical outcome or the physical state of our system. Okay, there's another kind of phase that comes up when we're talking about our qubit systems, and that's the relative phase. So here, let's say I have these two states, 0, 1 divided by 0 plus 1 divided by square root of 2, and 0 minus 1 divided by square root of 2. So this first state has an amplitude of 1 over square root of 2 for 1. And the second state has an amplitude of minus 1 over square root of 2 for the state 1. So we say that the two amplitudes differ by some relative phase. Their magnitudes are the same. They're both 1 over square root of 2. But their phase is different. So we say in general that two amplitudes, A and B, differ by a relative phase if A is equal to exponent I theta times B. So we say, again, for example, let's say two states that we looked at above, they're the same up to a relative phase shift because the zero amplitudes are identical. They have a relative phase factor of 1 plus 1. But the relative phase of the of the one states are minus 1. So they differ by this relative phase. And these relative phases are basis dependent, unlike the global phase. So states that differ by a relative phase give physically observable differences. So relative phases can be, for example, useful. They can carry information about the coherence of the system, for example. So we'll see more examples of that down the road. All right, the last concept in the formulation of quantum mechanics that we need to worry ourselves with when we're thinking about our qubit systems is this idea of composite quantum systems. So Postulate 4 is going to describe how the state space of a composite system is built from the state spaces of the component systems. And so it says that the state space of a composite system is the tensor product of the state spaces of the component physical systems. So if we have systems numbered 1 through n, the system number I is prepared in the state, and the joint state of the total system is the tensor product of the individual components, where this symbol here represents the tensor product. So you can ask yourself, why is the tensor product the mathematical construct that we would use to represent the state space of a composite system? And sometimes when people are describing this stuff, they just say, well, it doesn't matter. That's just a basic postulate. We don't care why it works or that it makes sense. It just is. Let's accept it and move on. Kind of way to rationalize it to yourself is through the idea of superposition. So in thinking about superposition of two states, so let's say x and y, I can say that they have a superposition that looks like alpha x plus beta y, and I can say that the absolute value of alpha squared plus beta squared is equal to 1. And by extension, if I have a composite system, it seems pretty natural to say that if I have some state, capital A, and some state, capital B, then there should be some corresponding state that we denote A times B, the product of A and B, of the joint system. And this is kind of how you get to the idea of tensor products from superpositions. It doesn't feel super satisfying to me, but that's how Nielsen and Schwang describe it, so we'll take it as at face value. Let's look at an example of what a tensor product is, because I feel like probably most people haven't worked with them, at least in a while. So I like this example of what a tensor product is. You want to think about tensor products as interleaving two vector spaces. So if I have a vector space V that has a basis chocolate ice cream, vanilla ice cream, and mint chocolate chip ice cream, and I have a vector space W that has a basis chocolate fudge sauce, caramel sauce, mango sauce, and raspberry sauce, then the tensor product of those two vector spaces are the linear combinations of the 12 possibilities. So we get every possible pairing when we take the tensor product. So we get chocolate ice cream with chocolate fudge, with caramel fudge, or with caramel, with mango, with raspberry. We get vanilla with all those, and we get mint chocolate chip with all of those. So I feel like that at least makes intuitive sense. You can look at this in a matrix form as well. So if we have two by two matrices, the normal product matrix that we talked about last week is equal to the new 2 by 2 matrix that you get by doing your row column math. But the tensor product is what you get when you take every element of matrix A and multiply it by matrix B. So from two 2 by 2 matrices, you end up with a 4 by 4 matrix. I don't think I gave you any tensor products on the homework, but we're always going to be dealing with these super simple 2 by 2 matrices, so it's not so bad. And we don't even need to really ever do it in practice. we're always just going to use a shorthand nomenclature for these tensor products. And we'll see a couple examples of that in this rest of this lecture. Okay, so not too scary. Oh yeah, if you want to read more about tensor products, I think Sutter does a pretty decent job in section 8.1, and I think Nielsen and Chuang even has something about it in the appendix of the book, so feel free to check both of those out. All right, so the cool thing about Postulate 4 is it is what enables us to define entanglement, which is kind of the whole point of quantum information. So if I consider the 2-qubit state that's written here, psi equals the state 0, 0 plus 1, 1 divided by square root of 2. What's cool about this entangled state is that there's no single qubit states, A and B, such that this new state is equal to the product of A and B. And we can say, in general, that the state of a composite system having this property is an entangled state. So a composite system that can't be written as a product of states of its component systems is entangled. So entanglement is a basis-dependent result of superposition. If I measure an entangled qubit, it will collapse it into one of its basis states with some probability, and measurement of one qubit will collapse the other qubit to a state that depends on the identity of the starting qubit state that the 2 qubits were in initially. And so this kind of state that we have written here is something known as a Bell state. It's one of 4 of the simplest orthogonal entangled states. We'll see the other ones in a minute. We're pretty much only going to work with Bell states when we're considering entangled states in this class, I think. Okay, let's look at a fun example. So there's this concept in information theory called superdense coding. And it's closely related to something we talked about a few weeks ago called quantum teleportation. So in quantum teleportation, that's the process by which a user can transmit 1 qubit using 2 classical bits. Superdense coding is a process where you can transmit 2 classical bits using 1 qubit. So that's our goal. Okay, so what does this look like? We get to bring in Alice and Bob and also Charlie this time. And so the kind of diagram that defines how we do this is written here. So we have, over here, we have our third party, Charlie. He's going to prepare and share a pair of Bell state qubits. He's going to send one of them to Alice, who's sitting here, and he's going to send one of them to Bob, who's sitting here. And what we want to do is let Alice send her qubit to Bob so that she can transmit, with the goal of transmitting 2 classical bits of information when Bob receives his 1 qubit from her. So before Alice can attempt to transmit these 2 classical bits of information using her Bell state, she has to apply a single gate operation based off of her intended message. So here's the setup. So I have Charlie, he sent 2 identical qubits that are a Bell pair, one to Alice, one to Bob. They look like that. And then Alice is going to send her qubit to Bob. But before she sends it, she's going to decide, okay, if I want to send Bob a 0, 0, my classical bits 0, 0, then I'm just going to send him my Bell state that's been modified by the identity gate. So nothing, I didn't change it, it's just identity. If I want to send him 0, 1, then I need to first apply a Z gate. If I want to send him 1, 0, I'm going to first apply an X gate. And if I'm going to send him 1, 1, then I'm going to first apply an I times Y gate. So we looked at the Pauli matrices before, they're up there. And so the states that will result after Alice applies these gates to her qubit, her entangled Bell state, are written here. So the Bell state times the I gate just gives you the same state. The Bell state times the Z gate gives you 0, 0, minus 1, 1. The Bell state times the X gate gives you 1, 0, plus 0, 1. And then the Bell state times the IY gate gives you 0, 1, minus 1, 0. I think there's another way to do this, maybe an X, Z, or something like that, some pair of gates rather than just Y. Okay, so Alice took her qubit, she applied her gates, and now she's going to send one of them, she's going to send hers that has undergone her gate operation to Bob. So Bob's pretty smart, and he knows that since Alice's qubits are entangled, the 2 qubits must be in one of the 4 Bell states. So once Bob receives Alice's encoded qubit, he's going to pass it untouched through his little reverse Bell circuit, which is down here. It's basically the reverse of the thing that Charlie did to prepare the Bell states in the first place. And that will decode Alice's message. And so Bob will obtain his 2 classical bits of information from Alice's single qubit. So it's a pretty clever design. And this is something that kind of has been demonstrated in the world to work. Okay, so we can recap the sort of 4 postulates, and we can kind of summarize them in a very simple way. So postulate 1 sort of sets up our arena of quantum mechanics, and it specifies how the state of an isolated quantum system is going to be described. And postulate 2 tells us that the dynamics of a closed quantum system are described by Schrodinger equations and by unitary evolution. So superpositions. And postulate 3 tells us how to extract information from our quantum system by giving us some rules for measurement. And then postulate 4 tells us how the state spaces of different quantum systems can be combined to give composites. And that's really all. There's more postulates of quantum mechanics, but those are all the ones we need to think about quantum information. Okay, so one of the things I asked you to read this week is from The Interpretation of Quantum Mechanics, from The Conscious Mind by David Chalmers. And what I love so much about his chapter, and the whole book, honestly, is that he very articulately describes what we just laid out in the 4 postulates in just a very clear and easy to understand way. And then he walks you through problems with the interpretation of quantum mechanics. So I thought that we might be able to spend a little bit of time talking through the interpretation of quantum mechanics, because there's some weird things there. And Nielsen and Twain brings them up sort of throughout their introduction to quantum mechanics, and we've kind of mentioned them a little bit in passing. But I thought it would be pretty fun to discuss. So let's start with sort of the thesis of Chalmers' text. What he says is that maybe quantum mechanics won't help us explain consciousness, but maybe a theory of consciousness will help us understand quantum mechanics better. And so that's the sort of motivation for this chapter of the book. And what he says is that the problem comes down to reconciling an issue between observership and experience. So trying to reframe the problems of quantum mechanics as problems about the relationship between the physical structure of the world, Schrodinger's equation, and our experience of it. It's discrete. Superpositions versus, well, it's one way. So quantum mechanics tells us that physical systems evolve linearly in a superposition, but our experience of the world is that the coin is heads. And so he tries to kind of unwrap this idea behind quantum mechanics requiring us to understand the universe through the lens of Schrodinger's equation and unitary evolution and probabilistic measurement. Okay, so there's many different interpretations of quantum mechanics. The first one, and the one that kind of is often out there most widely, and maybe it's the least problematic in a lot of ways, is the one that's written in the first bullet point. And that's, let's take the calculus literally. The world consists of waves. They evolve linearly in a superposition, and they occasionally collapse into a definite state when I make a measurement. Okay, I mean, that's kind of what we just went through. That's postulate 2 and postulate 3, and that's good. So the calculus is literal. The problem comes in when we think about this idea of making a measurement. Why would that be non-quantum? What about the measurement is unique? So his kind of problem as he's walking through this is he's like, well, what counts as a measurement? How does nature know when a measurement is made? Measurement is not some basic law of nature. And so various people over the course of the history of quantum mechanics have said, okay, well, maybe a measurement occurs whenever a quantum system interacts with a measuring apparatus. Maybe that makes it okay. The problem there is that it's just as implausible as the notion of measurement, right? This measuring apparatus, we now just need some criteria for what counts as a measuring apparatus, and like, why is that some unique, distinct thing that doesn't follow normal quantum linear evolution? So then another idea is, okay, instead of a measurement apparatus, what if I say that, what if I define the measurement apparatus as being a classical system? So I say that when my quantum system hits my classical system, that's when a measurement can occur. That's also problematic because this classical system can't be a term in a fundamental law of nature any more than a measurement can. So then there's other arguments. What if I say that when a quantum system interacts with a macroscopic system? But again, macroscopic, that's not some basic law of the universe. So it all is very, very arbitrary. There's no physical criterion for collapse that seems plausible, acceptable. So this is the conundrum that, well, Chalmers raises, but lots of people have raised about this interpretation of quantum mechanics. Okay, let's look at some of these other ones. So another interpretation, okay, before I move on. So Chalmers says that he thinks the only remotely tenable criterion that's been proposed for measurement is that a measurement takes place when a quantum system affects some being's consciousness. Right? He's a philosopher. He thinks about theories of consciousness. This is an interesting one, and it'll get way more interesting in a minute, because it kind of says the universe, was created in the Big Bang, whatever, and it was in a superposition, and it existed in a superposition until the moment that some consciousness evolved to observe it. Which is a funny idea. And I mean, it's very much related to the Schrodinger's cat thing, right? Like, the cat is in a superposition of dead and alive until you look. So before consciousness evolved, the entire universe was just a giant superposition. That's what he says would be required for that argument to hold. All right, so option 2 is try to get the measurement postulate for free. And I mentioned this a little bit last class, where there's some debate about, do we need postulate 3? Is it just, can measurement just be derived as some modification of postulate 2? So maybe measurement derives from the Schrodinger equation, and effective collapse is the consequence of something that he calls microscopic indefiniteness, meaning a fundamental probabilistic collapse would basically be replaced by an emergent statistical process in a complex system, so the statistics. The problem that Chalmers raises with this one, and other people raise, is that Schrodinger dynamics are linear, so it's always possible to construct situations in which these microscopic superpositions lead to macroscopic superpositions. So a superposed wave function evolves into a relatively clear-cut superposition of distinct macroscopic states rather than a jumbled mess. That would be okay. And maybe those macroscopic states decohere from each other with only minimal interference effects between them. So maybe. And then the other options are, okay, don't ask, it works. Maybe we're missing something, and there's some other fundamental postulate that's out there to be determined. And then the last one that he really spends a lot of time talking about and arguing maybe for is that the Schrodinger equation is all there is. I kind of think about this one to myself as turtles all the way down, superpositions all the way down. What does that mean? That means that in Chalmers' view, that means that superpositions extend all the way to our mind and the perception of them. So how do we frame this? Every time I make an observation, so let's think about spin up and spin down. I have some pointer that's pointing, telling me the direction of my electron spin can point spin up or spin down, and it's normally in a superposition until I look. And what Chalmers says is that maybe when I make this observation, I've created two distinct worlds in my mind. And so there's a lot of suggestion about split world theories and many world theories. And Chalmers says that this splitting worlds idea is maybe not what Everett meant when he kind of laid out this interpretation initially. It's really not a many worlds theory, but a one big world interpretation. There's one world, but it has more in it than we might imagine. So if there's any splitting, it's only in the minds of the observers. And as superpositions come in to affect your brain state, a number of separate minds result corresponding to the components of the superposition. That's the argument. Wait, so the Everett interpretation is something that existed long before David Chalmers came along to provide his lens. So you guys can read more about that. But he also gives a pretty detailed proof of how he rationalizes his sort of many minds version of the Everett interpretation. And he basically says that maybe it's good enough. But then in the end of his article, it's really fun. He just says that everything's crazy. And then none of it, if you if he had to, make a bet with God about if he actually believes what he wrote, he's like, I'm not sure I would do it. Which I love philosophers. It's good. the kind of thing they do at the end of their long treatises. But I do think that if you haven't read this chapter, it is worth reading because A, it brings up some interesting concepts, and B, it really does a beautiful job of distilling quantum mechanics to some very elegant language that, will give you 10 minutes worth of fun this weekend, maybe. So, yeah.